Hi, everybody. This is, as I said, this is part two of the of section 5.4, and we're going to sort of transition from Riemann sums to what we call the definite integral. So, the definite integral, and the difference between a definite and an indefinite, visually, is that the definite integral has a number down on the bottom and a number up on top, and that's the area, that's the interval that we're looking at the integral over. The definite integral basically is the limit of the Riemann sums, which means the definite integral is the area under the curve f of x. So if you look at a curve y equals f of x, and you're going from x equals a to x equals b, and you want to know the area underneath that curve. So this integral tells you the area underneath the curve at y equals f of x from the interval a to b. And that's what these guys mean. So let's look at an example of that. Let's look at an example. So here these are all A's and B's, but we'll get to ones with real numbers. So here we have a curve. This is our curve, y equals f of x, and that's x equals a, that's x equals b. So we're looking at the integral from a to b, and the area, so to speak, is a to b. The integral from, we read this, the integral from a to b of f of x dx. Now, why did I say the area, so to speak? Well, the reason is because region A, because it's underneath the x-axis, we say it has a negative area. If this was I have to emphasize this, if this was a geometry class, I would just say, oh, this is like 10 square inches or whatever it is. But it's not a geometry class, it's a calculus class. And therefore, when we look at area, we're looking, I guess, what you call directed area. Meaning, what do I mean by directed area? Well, if I go 10 miles an hour in reverse, so my speed is 10 miles an hour. I mean, I'm going 10 miles an hour, right? But my velocity, we say it's negative 10 miles an hour. You see what I'm saying? So that's the now, of course, if I push the pedal, if I push the gas more, and now I'm going reverse 15 miles an hour. So now my velocity is negative 15. Now, negative 15, of course, is a smaller number than negative 10. But we all know that if you crash into something, you're going to do more damage if you're going at 15 in reverse versus 10 in reverse. So when I'm looking at areas now, I don't know if I'm explaining, I might be over explaining this, but when we look at the integral from A to B, we're not getting region A plus region B. We're kind of getting the negative of this. So, for example, if this orange area is 10 square inches and this blue area is, 8 square inches, so the overall answer, the integral from A to B, is actually going to be negative 2 because it's negative 10 plus 8, which is negative 2. So just be aware of that. Just be aware of that. Now, let's look at some definite integrals. So I'm looking at this curve here. Now, this area A, this region A, is 2.33 square units. And this region over here, B, is 10.67. And this C over here is 5.63. Now, that's, again, we're looking at all these, we're listing these as positive because we're talking about areas like a geometry area. Now, the integral from A to B, so point A all the way to point B, well, it's 233 and 1067 and 563. However, since this is under the axis, it's really negative 233, and that here is negative. I'm sorry, looking at the wrong one now. I was looking at B, but it's number B, and that's negative 563. So if I want to go from A to B, it's negative 233 plus positive 1067, which gives me a grand total of 834. If I want to go from A to C, that's from here all the way to there, then it's negative 233 plus positive 1067 and negative 563, which is a grand total of 271. Notice the ones that are above the axis, I'm adding on positively. The ones that are below the axis, I'm subtracting off negatively, if you will. And now if I want to go from B to C, so that is from here to there, and that's just going to be negative 563 and pow. So that's the story. So a definite integral is the area. Now, we learned before the indefinite integral that we had in previous sections. So the indefinite integral and the definite integral look pretty much identical. The only thing different about them is that they have these numbers here. You see, there's the a and there's the b, but we'll replace it with a 3 and a 5, like if b equals 2 and c equals 3 or something like that. So it'll be the integral. So it'll be the integral from 2 to 3 or something like that. But there's a huge difference actually between a definite and an indefinite, in that the indefinite integral is a function. The definite integral is a number because it's just the sum of the total area. And even though you have, positive and negative and so forth. Let's look at some properties that the definite integral has. So let's go through this. The integral from a to a. Well, the integral from a to a, that's just a straight vertical line. So that's basically the area under a curve, but the width of it is zero because it's just a straight vertical line. That's why the integral from a to a is always going to be 0. Now the integral from a to b is negative the integral from b to a. So not only do we say that if it's underneath the x-axis, it becomes negative, but if I reverse direction, it becomes negative. Because like I say, we're not just talking about area, we're talking about directed area. That's why, again, if this was a geometry class, there would be no positives and everything would be positive. There'd be no negatives here. But but since we're not looking at that, we're looking at it from a different perspective. We're looking at the directed area, so it could be positive, it could be negative. The integral from a to b of k f of x is equal to k times the integral from a to b of f of x. And this is very similar, this idea of pulling a constant out. We learned you can pull a constant out of a limit. We learned you can pull a constant out of a derivative, and now we're learning you can pull a constant out of an integral. We actually learned that about indefinite integrals, and it's true about definite integrals as well. So all these things are true. The integral of the sum is the sum of the integrals. I could break something up. The integral from a to c, well, I could break it up into a to b plus b to c. We're kind of doing that actually in the previous example. I just wasn't really saying it this way. But you can break the integral up into smaller, bite-sized pieces, if you will. So let's look at this guy right here. We want to look at blah, blah, blah. The integral from 0 to 2 of x dx is equal to 2. And the integral from 0 to, now they're just giving us this information. I'm not going to explain why this is. Not that hard to know why this is, but right now they're saying if given that this is all true, which which of course is true. We lie to you here. So the integral from 0 to 2 of x squared is equal to 8/3, which means if I have a parabola and I'm looking at the area underneath from 0 to 2, it'll come out to a grand total of 8/3. And the integral from 2 to 3 of x squared is equal to 19/3. That's just is. So let's just take that as a given. And now let's look over here. So we have a bunch of things we could see from this. So given these 3 facts here, we're gonna use them to determine some other integrals. Now we're gonna look at the integral from 0 to 2 of 12x squared dx. So that is equal to 12 times the integral from 0 to 2 of x squared dx. That's one of the properties that we just learned on the previous, just 2 minutes ago. Now, this integral here is equal to 8/3 because we have that right up here. So it's 12 times 8/3, which comes out to be 32. Now, next one, b. The integral from 0 to 2 of 2x minus 6x squared. Well, first of all, I could break this up into 2 integrals, and then I could also I could take out the 2, and I could take the 6 out of the integral. So this becomes 2 times the integral from 0 to 2 of x dx minus 6 integral from 0 to 2 of x squared dx. Now I just plug in the numbers. So this is 2 because it's given here, and that's 8/3 because it's given there. So it's just 2 times 2 minus 6 times 8/3, which if you crunch that all out, comes out to be negative 12. Next, the integral from 3 to 2 of x squared. Well, we know, again, from one of our properties, that the integral from 3 to 2 is negative the integral from 2 to 3 of x squared, and which Now we know the integral from 2 to 3 of x squared is 19 thirds because it says it up here. Hence, this is equal to negative 19 over 3. And this one here, I'm not even going to look at, once I see 5, 5, I know the answer is 0. Because whenever I go, this will literally be like taking some curve and just drawing a straight line under it and say, what's the area in that line? Well, the area in the line is 0, and that's 0. And finally, my last one, the integral from 0 to 3 of 3x squared. Okay, well, we're going to use the fact that we know from 0 to 2, and we know from 2 to 3, and we're going to use that. But I also have to deal with this little 3, this coefficient of 3 that's in there. So first thing I'm going to do is pull the 3 out, and then I'm going to split this into 2 integrals. Even though x squared is, I'm not going to split up x squared, but the 0 to 3, the limits of integration can be split. And I have the integral from 0 to 2 of x squared, and the integral from 2 to 3 of x squared. So the integral from 0 to 3 can be broken up into 2 to 3 and 0 to 2 and 2 to 3. Anyways, I know that this is equal to 8 thirds because it's given up here. I know that this part is equal to 19 thirds because it's given up there. So I have this 3 times 8 thirds plus 3 times 19 thirds, crunch, crunch, crunch. And that gives me a grand total of 27. And that's how I'm using properties. So in other words, I don't have to reinvent the wheel. Once I know these 3 facts, I could use that to figure out all these different complicated integrals. And without doing any new original work, all I'm doing is kind of like adapting what we already had. Well, that's the end of 5.4. Hope you enjoyed it hope you enjoyed as much as I did. And I will see you guys for the next for our next exciting video. And here I am. So, oh, you never saw me this whole time like that. I'm so sorry. Here I am. I didn't realize that my video was off. Anyway, here we go. I will see you guys next time. Bye, everybody. Have fun.